Here, and this is a calculus solution to the 2020 AMC 12B problem 22. Here's the view of this problem. What is the maximum value of 2 to the t minus 3t times t over 4 to the t for all real values at t? For real values at t. Okay, so if we were to use calculus, we actually have a pretty straight, clear approach on how to do this. We distribute the t, and then we apply the quotient rule to find the derivative, set it to 0 to find critical points, and then test them to find the maximum value, right? So let's apply that strategy. Let f of t be the function in t of t times 2 to t minus 3t squared of 4 raised to power t. Now we have to use the quotient rule, and in fact what I'm going to do in this video is I'm actually going to derive the quotient rule as well. And to do that, we actually need to have a prerequisite in the product rule as well as the chain rule. I'll just leave these as like prerequisites. So f of x times g of x, we need to know that the derivative of this will just be equal to f prime of x times g of x plus f of x times g prime of x. And then for the chain rule, I'm pretty sure to derive this, all you have to do is use the first principles definition of the derivative. And then for the chain rule, you can also do that similarly, or I think you can also plot through like epsilon and delta definitions for that also, which is a little bit more technical. So let's just use this as a prerequisite and derive the chain rule. So f of x over g of x, we want to find an expression for this. Well, first of all, g of x is in the denominator. Let's kind of put it in the numerator so we can apply our product rule. F of x times g of x raised to power negative 1. And this is just a product rule. We just now do f prime of x times g of x raised to power negative 1 plus f of x times g prime of x times g prime of x. That'll give us negative g of x raised to power negative 2, but we have to multiply by the derivative of g if it's more than like a linear function or something. Okay, and then now let's kind of like get this under common denominators and stuff. So we have f prime of x over g of x plus this becomes 1 over g of x squared. So we can write this as negative f of x times g prime of x over g of x squared. And what we can do is we can get a common denominator and get a final expression for this. So we have g of x times f prime of x minus f of x times g prime of x over this becomes a square because we multiply by g of x, so g of x squared. So we have an expression for the derivative, and I'm actually going to derive another thing because why not? We actually see some stuff 2 raised to power t and 4 raised to power t. So let's try to derive something for the derivative of a raised to power t. So how can we do that? Well, a to the t by itself we can't do anything interesting, but what we can do is do a, and then we can do log base e of a raised to power t, right? This will give us a raised to power t. Good. So now the only reason we're doing this is so we can bring this t over to get a raised to power t times log base e of a. Okay, and then now how can we differentiate this? Well, this is actually just a constant. Log base e of a is just a constant, so we can apply the chain rule to get log base e of a times a raised to power t times log base e of a. But precisely if we bring the t over, we get log base e of a raised to power t, which is just a raised to power t. So this is just log base e of a times a raised to power t. So we've derived 2 useful formulas to solve this question. So now let's actually get into solving this question. So using the product rule and this above theorem, what we have to do is we have to differentiate this. So this becomes, this is what? This is g of x. This is our f of x. So we have g of x, 4 raised to power t, times f of x, times f prime of x, which is if using the product rule on this, we get 2 raised to the power t plus t times ln2 times 2 raised to the power t, and then we have 6t, because we have to differentiate this part over here. And then what we have to do is we have to subtract f of t minus t times 2 raised to the power t minus 3t squared. And then we have to multiply by the derivative of g of x, which is nothing but ln4. ln4 times 4 raised to the power t. Okay, and this whole thing is over g of x squared, which is 4 raised to the power 2t. Okay, and then now what we have to do is we have to set this to 0 to find critical points. And now we can multiply both sides by 4 raised to the power t. Okay, wait, hold on. Okay, so this is equal to 0. And then now maybe we can bring stuff to the other side. So we have another sheet. 4 raised to the power t times 2 raised to the power t. And then it was like plus 2 ln2, plus t times ln2, t times ln2 times 2 raised to the power t, and then minus 6t is equal to, we can bring this over. This gives us t times 2t minus 3t squared, minus 3t squared, and then times, and then times ln4. I'll write that as 2 ln2 times 2 ln2 2 times 4 raised to the power t. We see that the 4 raised to the power t's will cancel. So 4 raised to the power t over here, and then 4 raised to the power t here cancels. And then now we're almost done. We can leave this the same. 2 raised to the power t plus t times ln2 times 2 times t minus 6t is equal to 2t times 2 raised to the power t times ln2, and then minus 6t squared times ln2. Almost done over here. We see these terms over here are kind of similar. They're actually exactly similar. So if we bring this over, we get negative t times ln2 times 2 raised to the power t. We can factor out 2 to t to get 2 to t times. This becomes 1 minus 2 ln2. 1 minus ln2. Let's see. 2 raised to the power 2 times 1, 2, t times ln 2 raised to the power t. One minus t ln2 is equal to 6t times 1 minus t times ln2. Okay, and now we see that these conveniently cancel out, so we have 2 to t is equal to 6 raised to the power t. So we can plug this in over here. 2 to t is equal to 6t, right? So this gives us 3t squared over 2 raised to the power t. That's 4 raised to the power t is just this thing squared, which is 36t squared. Cancel this and simplify to get 1/12 c, and we are done.